before to dive in my presentation, I would like to mention who are the partners involved in this project. We have Umicore, Finland, and the Aalto University who are collaborating with me, and they are providing me the samples to analyze. And all the samples will be analyzed and characterized at TSRF, the facility I will do my PhD, of course. So my project, as the title suggests, is on lithium-ion batteries. What is a cell? We have an electrochemical system which has main components, different components, a negative electrode, a separator, and a positive electrode. And all these elements are soaked into a liquid electrolyte. When we charge and discharge the cell, the lithium is shuffling between the positive electrode and the negative electrode, producing electric current that we can use. My PhD project is focused on one of the components, the positive electrode, and I will work with the commercially called NMC811, which Umicore produces. And it is a transition metal oxide with a layered structure where the lithium is intercalated between these transition metal layers. Why this material is so interesting is because we have a low cobalt content. The cobalt is going to be more expensive in the future, and we want to remove or completely remove it. And this electrode has high energy density, which means that our device or our vehicle can travel for longer distances. Of course, we have problems. It's not everything shiny and bright. So as I said before, we are moving back and forth the lithium in the structure. This caused a few problems during the charge and discharge of the cell. We have a structure instability because of this, but when we are at high voltages, the active material degrades the electrolyte. These two main problems leads to a fast capacity fading we see here, which means that we need to change the battery pack as soon as possible. What we want to do is to stabilize this system to avoid this degradation. So to face the problem in material science, usually the doping is the way to go for. You see a picture in the on the electron microscope, the outside of my particle on the left and the inside of the particle on the right. The doping strategy we want to use is to dope the material with zirconium in a wide range of concentration by powder calcination. We want to go for zirconium because we think that we could have a double effect. The idea is that if the zirconium is included in the crystal, will lead to stronger bonds, which will possibly improve the stability. And also we'll have a coating protection between the electrolyte and the active material, which will protect the particle from the electrolyte. We have two questions. Is the dopant forming a coating structure? Is it like diffusing inside a particle and affecting the crystal structure? Or is doing both? To answer these questions, we can use a powerful tool called powder diffraction. And this is available at TSRF. And with the EBS, the new upgrade, we can get information, excellent data. Especially if we want to look at differences in low doping concentration. When we analyze this data, we see that as a function of the doping, the unit cell is enlarging, is like expanding. And if we look at the 5% of doping, the highest doping concentration compared to the lowest one, we get a similar expansion of the unit cell. But however, when we look at the features of the 5% in the powder diffraction, we see things that we cannot see in the other samples. We have a multiple phase formation, we lose intensity, and the peak splitting is not well defined as the other sample, and the peak broadening for the 5% is higher compared to the other sample. We can do some observation with this data, is that the doping is leading to a unit cell expansion, is modifying the crystal, and potentially we can have better lithium diffusion, improving the performances of the system. But when the doping is too much, we are introducing disorder and we are also losing crystallinity, which means that we have to rescale the doping, and we cannot dope too much the material, which is quite obvious. The coating could be amorphous, so it's not easily detectable by diffraction. So what could be, what are the next steps? The next strategy is to use quantitative analysis to check either the zirconium amount and to characterize the surface. And I'm testing right now some some cells, some batteries, to correlate the electrochemistry information with the observation we did. Thanks to you all for the presentation. And I would like to thank the ID31 group that helped me a lot for this analysis.